In 1993, the model for advancing gender diversity in STEM at Rutgers was born. Since then, Project Super undergraduate research program has served countless Douglas students, providing them the opportunity to conduct funded laboratory research under the mentorship of Rutgers faculty. This direct experience in competitive STEM fields has not only impacted individual students, it has forever moved the needle for gender equity in STEM at Rutgers. As we celebrate the 30th anniversary of Project Super, we sit down with longtime Super mentor and chair of the Materials Science and Engineering Department, Dr. Lisa Klein, and two of her Project Super summer research students, Abigail and Paloma, for a conversation. I'm Meghan Rehbein. I'm the Dean of Douglas. I've been in this role since July, and I'm thrilled to be here with you to talk about the 30th anniversary of Project Super and some of the research you're doing. Dr. Klein, I'd love to have you introduce yourself.
Hi, I'm Lisa Klein, and I've been a part of the Douglas project since 1996. I've been at Rutgers since 1977, and it's been a great experience being part of this.
I'm Abigail Schoeffler, and I'm a second year in industrial engineering, and I'm working on flame retardancy in Dr. Klein's lab.
Wow.
I'm Paloma. I'm a rising sophomore majoring in biomedical engineering, and I'm working on implementing aerogels to aid in oil spill cleanups.
Wow. So, Dr. Klein, tell us a little bit about the research that's going on in your lab and what you're doing with Project Super this summer.
The topic I research is solid gel processing, and it's a method for making glass and ceramic materials by combining chemistry and generally using low temperature processes to make materials that otherwise would require very high temperatures. And this summer we have focused on aerogels. So aerogels are very lightweight materials. The students have been making some of their own. They've also been using some previously made aerogels. And we take this material and we see what applications we can find, and we've been having a lot of fun.
What have you found so far?
Well, I've been setting stuff on fire is my project, and I found a lot of different colored flames, which was unexpected. I've gotten green flames and pink flames I actually saw. But I've been putting different chemicals into the aerogels to see how that affects flame retardancy, and some like magnesium oxide have really improved.
Wow. So what will that do in the future? So an aerogel then is more, you can use it in more places because it's more flame retardant.
Mm-hmm. So aerogels that are super flame retardant could be great for stuff like insulation or a firefighter's clothing. Basically anything that needs to be flame retardant or a great insulator, aerogels are a good solution.
That's great. How about you? What are you finding?
So I found that because of the aerogel's hydrophobicity, it's really great for cleaning up oil spills because it's not attracted to the water, it's attracted to the oil because the oil is also non-polar. And for that, it's really great because there are so many different methods for cleaning up oil spills, but it's very complicated depending on the oil type or where the oil is located. So I've been using different kinds of oils such as canola oil and 3-in-1 oil, baby oil, to see how the aerogel reacts and what type of texture of aerogel is best for that.
Wow. So this all has to be pretty impactful. You know, what's the implication of some of this work?
So I think in general, the aerogel materials have been proposed to replace other insulation materials. So for example, we insulate our homes with fiberglass. Mm-hmm. And fiberglass is great, but it has to be made at high temperature to make the fiberized glass. And then we put it into, the space in the walls for insulating homes, and it requires about 6 inches. And another problem is, over a long period of time, fiberglass kind of settles, and it also has a tendency to create dust. These materials are blocks, and for what we'd ordinarily use 6 inches of fiberglass, we'd get the same insulating power from just 1 inch. So that would mean more usable space. We could slide it into homes as they're being built. It doesn't have a tendency to compact or dust, so that's an advantage over fiberglass. And especially if we can make it so that it has no tendency to flame when a house goes up in smoke. We don't want to have any dangerous chemicals evolved. So that's where Abigail's project fits in. It's also been used for containing oil spills, so that's where Paloma's project fits in.
So what we're doing in the lab today is we're gonna drop some oil in here and sort of create some kind of like oil slick simulation where we'd see what the aerogel actually does to it when it's encountering oil. So we have about 150 milliliters of distilled water, so we just pour that in there.
That's your ocean.
This
And
is
you're
our
gonna put
ocean.
the oil spill in the ocean.
Yep. And then we just take this. If I can remember how to open this. Okay, that didn't work.
It's gonna be hard with the gloves on too.
It is gonna be hard with the gloves.
There it is.
Yep. Okay. So I usually get it to be about like covering it just enough. I usually use about 27 grams of oil. I think that.
What kind of oil is that?
This is the 3-in-1 oil.
Mm-hmm. So things people have in their house.
Yep, this is the household oil. So I'm just pour that in there. And then we're gonna walk over to the to measure its weight. This is sample number 7.
And you're weighing it.
Right. And then I take that number and I walk over and I record it. So this is 0.382 grams. And then we just record that in our data. In my table, I have the initial weight and the oil type. Okay. And then we do that for the rest of them. And this is sample number 8. I also write down on the wafer paper what types of oil I've used so far.
So this says grape oil and baby canola.
Yeah, those are the 3 different oil types that I've used so far. 741 grams. The interesting thing too is because I've used these already, they still tend to hold on to that oil weight even though like it's already been in there for like 3 weeks. And then we do the last one. So now that we have the weight recorded, we just drop them in there. So
And you're putting them right in the oil.
just right in there. And this is the last one. Yeah. And I like to move it around just so that the oil kind of goes around. And it's pretty much what it ends up looking like.
Yep, and they're kind of floating in it, and they
And you'll
attract
notice
the
that the oil kind of wants to move closer to the aerogel. It'll kind of try to absorb it.
Oh yeah, it looks like a little boat.
Yeah, you can kind of see it's already moving. So
Yeah.
that's how you know it's working.
And does the color of the aerogel reflect that it's absorbed oil at this point?
Yeah, actually, you can kind of see it in some of them. They were initially clear. The aerogels are transparent. So with some of them, like this one, that is completely yellow because I've been using them for quite some time.
Right.
So it's interesting to see how they sort of change over time.
Mm-hmm.
And these are all the samples that I've used so far.
So how long will you wait before you come back and see what each of these?
I usually wait for about a day. I come back into the lab. I would retract them with the, I forgot these are called.
Well, I call them tweezers,
Right,
but I don't know what they're called
tweezers.
in the lab.
I would use the tweezers and I would take them out of the oil and I'd sort of assess how much oil I can see is left in there. Typically, there's actually no oil left after I do these. It's very
And
interesting.
that's 24 hours.
24 hours.
That's amazing.
Yeah.
What a difference that could make.
I know.
In an oil spill
Crazy
in the
if you think
ocean
about
or-
the future of,
Yeah.
you know.
Very cool. Thank you for showing me.
Yeah, anytime.
So, can you tell us about your first experience as a mentor in Project Super?
In 1996, there was one of the earlier versions of the course. It required the students, freshman year, to take the Introduction to Scientific Research, which is very important, and also allowed students to have an experience working in the lab. And I think that doing an independent project is one of the things that I know in my own case, being able to do an independent project was what sealed the deal. I knew after that I liked doing research. I wanted to stay in a technical field. I liked trying things out and improvising and coming up with original solutions. To me, getting involved in a research project is what sustains especially women students in undergraduate engineering and science fields.
And why have you continued letting Douglas students into your lab?
Well, they're the best.
I agree.
The structure of the Introduction to Scientific Research is an excellent way to make students understand the importance of research, to get involved in it. I like the fact that they meet with their peers, other students. They need to learn how to express themselves and explain what they're doing, and have, you know, a hypothesis and an approach and a method and try things out. To have that kind of structure along with the opportunity to be in the lab is really how to get people excited.
Tell me about what you're doing, because this looks very cool.
So I am doing flame tests, which involves turning on this Bunsen burner here and then putting it under the sample and seeing how much the sample reacts or is good for not reacting at all. Right. So I'm just going to turn on the gas, which is a little finicky, and then I'm going to spark it. And then you can see my flame, which is very nice and blue. It's got a little orange bit. And then I'm going to put it under the sample and leave it there for about 15 seconds. And you can see it is reacting.
But just a little.
Just a little. It reacts more as time goes on. And you can see all the cracks that's going on right now.
Oh, yeah.
Yeah. And then, since it's been about enough time, I'm going to take it away. And then I would ordinarily take, oh, see, it's caught fire.
Yeah.
That's what you don't want to happen.
But it gives you
So
just
that's
as
what
much information.
It does, and it's also fun to watch, and you see how long it takes to self-extinguish.
Yeah.
This is an untreated sample, obviously.
Right. Right. But that's part of what you're looking at. What treatments on the aerogel may get more or less flame retardant. So
Yes.
it's always good to know what you're starting with.
Yes, and
It looks like it's
you
going
can see a
pretty
little
well.
amber on it. Yeah, so that's one of the most flammable samples that I've seen, actually. It seems like the entire thing has caught fire.
Yeah. And it's keeping going.
Yep, I think the longest I've had before this was 30 seconds before it self-extinguished. This might take the cake.
Oh, it looks like it's going.
Oh, it's
No,
still
there
going.
it is.
So this was a sample that was just made a while ago in the lab. I just put it in there because I figured you could see the cracks, but it's...
And it's so a very different color now that it started.
Yeah, so a lot of them, they turn like brown if they're just a little bit but this one, it's kind of
charring.
black.
Yeah, it's charring all the way. So even though an aerogel doesn't turn into dust normally if it's exposed to fire, it does break down, right?
Well, as you know, I've been really happy to be part of all of these programs that have run through Douglas. And as I was saying to the students earlier, when I first came to Rutgers, Douglas was my refuge. I used to go over there when I needed to see women. There weren't enough of them on the Bush campus, and it was an opportunity to talk to women in all different fields and get their perspectives on how we were going to encourage women students to persevere. So knowing that Douglas has this legacy of incorporating feminist education in their goals, and that overflows into those of us that go into the lab sciences, how do you see the continuation of that effort at Douglas?
So Douglas has gotten to a place where 50% of our students are majoring in a STEM field, which is amazing. It's 1,000 students every year who are preparing for careers in sciences or in tech or even in math, which not as many in math, but and we want to continue that. We want to grow it. I think that one of the things that Douglas and our partners around Rutgers, including in the School of Engineering, have always been focused on is looking at who's in the room and trying to help the people that aren't in the room get in the room. Because one of the things we know is that who's in the room drives what questions get asked. And so if you are a homogeneous group of people, you're asking the same questions over and over again. And when you bring diversity, when you bring women into a lab that hasn't had women before, or you bring students of color into a lab that has been predominantly white, or when you bring people who come from backgrounds completely different into the lab, they're asking different questions. They're approaching. Look at any of our programs, every single one of them needs an institutional partner, whether it's the School of Engineering, whether it's you, Dr. Klein, or whether it's something wider like the Academic Master Plan. But we are never doing anything alone. So I think that's probably a little bit of our feminist legacy as well, that we're not trying to do anything alone because we know we're stronger together doing this work.